Hello and welcome back. This is the penultimate lecture for Computer Science 2. Of course, it's Dead Week. Only 2 lectures to go. And today we'll be picking up where we left off last time. We will be looking at, we were looking at binary search trees before. And what we'll be looking at today are not balanced binary search trees, but something very closely related to them. The motivation here is that the binary search trees that we looked at before, they're nice if they're somewhat balanced, because then you have a guarantee on the depth of the tree being logarithmic. Unfortunately, that's not necessarily the case. Binary search trees by themselves are not necessarily balanced. You can have what are called degenerate trees. And to demonstrate that, let me go ahead and go over to the main screen here. And what I've got over here is our old binary search tree implementation over here. But I've set up a demo here to hold a binary search tree with a bunch of integers. And what I'm going to do is I'm going to insert integers 1, 2, 3, 4, all the way up to 10. All right, and then I'm going to print it out and let's see what it looks like. Well, that's a degenerate tree, because what ends up happening is 1 becomes your root, and then you just simply 2 becomes your right tree, right child, 3, 4, 5, going all the way down to the line. So this depth here is going to end up being 9. So if we've got 10 elements in there of 10 nodes, then we could have a maximum depth of 9. In other words, if we've got n nodes in general in there, we could have a maximum depth of order n. And hopefully this looks kind of familiar here. This is nothing more than a linked list. So in the worst case, binary search trees can degenerate into linked lists, and we're back at square one. Okay. So how do we address this? Well, there are what are called balanced binary search trees. AVL trees, 2-3 trees, red-black trees. There are at least a dozen, maybe 2 dozen different types of balanced binary search trees out there. That goes beyond this course. Basically, the way that they work is by rebalancing themselves. So if something gets too skewed to the right, then what you can do is you can pull it out over, and then it becomes balanced again. We're not going to look at that, and instead we're going to look at something related that does have a guarantee on its balance factor, or that it's going to give us a guarantee on the depth of that tree, called heaps. Now, we've already seen stacks, both in the context of programs. You have a call stack so that you can keep track of the breadcrumbs of function calling, so that you can return to those functions. Stacks, the word stack kind of gives you the impression that it's a very organized stack. It's a nice stack. What is a heap? Well, a heap is kind of like a pile, a less organized, less structured heap of stuff, right? A pile of stuff. And so that's what we're going to look at today. Over here we've got an example. This is called a min heap. But let's go ahead and define this. So a heap is, oops, let me go ahead and use this keyboard, is a data structure that holds stuff. Actually, instead of just calling it a data structure, let's call it what it is. It's a binary tree. Is a binary tree that that has the following properties. Now I'm going to simplify this so that there are only 2 properties. Sometimes some authors will separate it out into 3 properties, but it is full. It is a full binary tree. Right? That means that at every level, every node is present, except possibly, and like in this example over here, possibly the last row, which is full to the left. So conceptually here, over here, we've got a heap. It's full. Every level up to that, every single node is present. And so you can phrase this another way, that every from levels 1 through whatever, everything has a child, both children, right? Except for possibly the last level. And the last level here, it's full to the left. Okay. So if I were to add a node over here, right, and put whatever is in there, that would no longer adhere to the fullness property. This would no longer be a full binary tree because we've got a gap here. Or if I were to put something over here or wherever else, right? So that's a fullness property. And because of that fullness property, we have a guarantee on the depth. The depth is going to be logarithmic, right? So as a note here, this guarantees that the depth of a heap is order log n. Right? Great. But unfortunately, we pay a price for this as far as the heaps go, because there's another property here that it satisfies the heap property. Heap property. There we go. And satisfies. There we go. Don't need to spell check here. I'll spell check it later. It satisfies the heap property. The key in any node is less, and this is the min heap property, than both of its children. So this is not a binary search tree. As you can see right here from this example, this is definitely not a binary search tree. Both the children are greater. In other words, the key value here at the root is less than both of its children. Another way of saying that is both of its children have a key value that is greater. Of course, you can flip that property if you want to, and you have what's called a max heap, right? But what we've got here is a min heap, and that's what we'll stick with here. And it doesn't really matter because any implementation, you're going to do this with a comparator anyway. And so all you need to do is flip your comparator, and you've got a different comparator, and now you've got go from a min heap to a max heap or back and forth. It depends on what you're storing into this heap. Okay, so we've got a nice min heap here, and if you look at all of the heap property is satisfied for all of these things. Okay. So let's go ahead and make some observations. I'm using this keyboard today because I've lost my S key. Right? So you would not believe how many times the letter S comes up in the English language. So observations. Well, first of all, we can move this observation down here. That this guarantees the fullness property guarantees the depth of the tree is logarithmic. Right? That D is order log n. All right, so that's a very nice thing to have. But the other observation here is what's at the top of the heap, and by the top we mean up here. Right? What's at the top of the heap? The root node. This is the top of the heap. Right? Contains the minimum element in the heap. Right? So again, the reason we look at data structures and all data structures is so that we can exploit the structure in the data structures. So how can we take these two properties and exploit them and get some sort of a very, very good performance out of our heap that we've defined here? Right? So we're going to actually support only two basic operations. Right? Heaps, you can do more if you want, and you can do secondary like we did with lists and with trees and stuff like that. But heaps basically support two basic operations. Right? One is get min. I'll do it like this. Get min, which retrieves and removes the minimum element. Of course, you can do a peek as well and retrieve it, but not remove it from the heap. And two, insert. Right, adds an element to the heap. Right? And of course, with both of these, we're going to want to make sure that before and after that it remains a heap. That is, if we're going to insert something, we need to make sure that the heap properties are satisfied. It has to be full. Except for possibly the last row, which is full to the left. and it has to satisfy the heap property, that both of its children are going to be greater than the node itself, right? For all nodes. So how are we going to achieve these, and how are we going to make sure that they are efficient? So first of all, let's go ahead and talk about get min. Right? Well, when you have a binary tree, you start at the root, so we're already there, right? We'll save the way that I'm going to get min is I'm going to save the root's element, I should say, to return as a value, right? And of course, if it's a peak instead, then you're already done. You can just go ahead and give a copy of it or something like that, okay? But once this is gone, right, if I take this out, then I'm left with two trees, which can be a forest. I need to recombine them some way, right? And so I could potentially move something up, right? I could move 5 up. I couldn't move 7 up because 7 would be greater than 5, right? So consider having removed this one. You could move 7 up, but then it would be greater than 5, and that would violate the heap property. Okay, well, I'll go ahead and just take the minimum every single time here. Okay, well, that means that 5 gets moved up here, and maybe 5 is an element up here now. Well, that means that I've got another gap, and I've got to solve that problem. Well, if I do the same thing as before and promote the minimum child, then 8 comes up here, right? And now I'm left with this, and now I've got no children left to promote up. And so I've got a gap in my heap. And so in my efforts to try to make sure that the heap property was satisfied, I've now violated the fullness property. So let's not do that, right? So instead, let's look at it from the other angle, that I want to make sure that I preserve the fullness property first. Well, to preserve the fullness property, that means that I can, if I'm going to get rid of 2, then from the topology of the graph itself, I can't remove an internal node here. I don't want to remove the root node because we saw what happens with that. So instead what I'm going to do is I'm going to go to the very last node. And by very last node, I mean go to the deepest level of the heap, go all the way to the right, and remove that element, right? So remove the last node. And again, by last, I mean the node at the deepest level all the way to the right. If we have only 1, 2, 3 levels here, then it would be this would be the last level, and that would be the last node. Okay, in that level, all the way to the right. All right. So let's go ahead and do that. I'll cut that off, and now I've got 20 sitting out here. Of course, I've saved off 2 already to return it. All right. So I need to remove the last node. Once I've done that, though, now I can solve my gap problem up here. What I can do is I can put 20 up there, and with this gone, now my fullness property is satisfied. But again, same problem as before. By favoring one of the properties, now I've violated the other property. So I'm satisfying the fullness property, but I'm no longer satisfying the heap property because 20 is greater than both of its children. So what I can do is, this is step 1, step 2, promote. I will do this. I will promote the last node to the root. Then 4, I will heapify it. Right, very technical term. Right? Heapification simply just means pushing 20 down until it's where it needs to be, and pushing it down until the heap property is satisfied. So now I will take the idea that I was working with before, and what I'll do is I'll promote up the minimum child here, but not just promote it up. What I will do is I will swap these two. So this becomes 20, and now this becomes 5. Okay? I'm doing this in pencil because I do want to erase some things, right? So I ended up making a swap, right? What I needed to do is I needed to make sure that the heapness property was violated or satisfied. and by heapifying. And so I looked at both of its children. I took the minimum, and the minimum is greater than or is less than 20, so the heap property is violated, and I end up swapping. Now 20 is down here. The heap property still is not satisfied. It is we've got both the children here that are less than 20. So I continue. I promote up the minimum child, and now 8 is up here, and 20 is now here. Okay? At that point, there are no more children. 20 has been heapified down the heap until it satisfies the heap property. We have 5, 8, and 20. Right? Now, you can make a really quick observation here that, well, how many comparisons am I going to make? How many swaps am I going to make? Well, if I have free access to both the root and to the last node, then these two things are going to be constant time. All I need to do is save this off into a variable. All I need to do is save the contents of that node off into a variable, remove that node. That's all constant. Promoting it back up to the root, well, I've already got free access to that, so that's also constant. The heapification is where all the real work is done. The heapification might end up pushing this value down all the way to the bottom of the heap. But remember from our first observation that the depth of the heap is going to be logarithmic, and so this entire process here is also going to be logarithmic, under the assumption that we have access to both the root and the last element here. Okay? And we'll talk about that assumption later on here. Okay? All right, well, what about the other one? What about the insertion method? Okay? Here we go. I've got another version. Here, what I'll do is I'll use another piece of paper over here so that I can write over here. Right, there we go. What about insert? Right. Now, I've rolled this back here. Hopefully you can still see them. But otherwise it's 2, 5, 7, 10, 8. Let's go ahead and insert. Yeah, let's insert 100. Let's insert 1. Right? So where does it need to be? It needs to be up here because 1 is less than everything else in here. So 1 needs to be the new root. Well, I could make a new root, right? I could make 1 and then make that the left child. But now I've violated the fullness property again, right? This entire right subtree of 1 should be there. Right? So again, let's go ahead and take the strategy here of trying to fulfill the fullness property first. If I fulfill the fullness property first, what I need to do is I need to insert it as a new node in the next available spot. And by next available spot, what I mean is you go down all the way to the bottom of the heap, and all the way to the left, and this first available spot right here is the left child of 8. Right? So what we're going to do is we're going to insert 1 there. And you can see that the fullness property is satisfied. Okay? But the heap property is no longer satisfied. The heap property means that I need to, again, heapify, but in the in the other direction. I'm going to heapify it upwards. That I'm going to simply just swap and promote it until it's where it needs to be. I look at its parent and I see that the parent is greater, so what I need to do is swap these. And 8 comes down as the new child, as the new left child of 1 here. Right? So swap. I look and is the heap property satisfied? I just need to look at the parent now. I don't need to look at both the children here because I'm heapifying upwards here. So the heap property is not satisfied because 5 is greater than 1. So I will go ahead and swap them. 5 is now down here and 1 is now here. 1 and its parent are out of order because 1 is less than 2. So I need to swap them again. And at this point, it becomes the new root, and I don't have to do anything more. Now, if I were to, if I were as another step here to insert 100, 100 would then become the right child of 5. The heap property is immediately satisfied here, because if I look at its parent, it's less, and so I don't need to do anything. Sometimes you get lucky, and you don't have to. You have to do one comparison and no swaps. Sometimes you get unlucky, and I have to make 1, 2, 3 actually 4 comparisons here, if you count checking to see that it's the root, or you can put that into your while condition. But otherwise, 1, 2, 3 swaps. So 3 comparisons, 3 swaps. In other words, in the worst case, it goes all the way back up to the root. And I don't have to do anything beyond that. In other words, and again, the fullness property gives us that the depth is going to be logarithmic. Both of these operations that I've covered so far are proportional to the depth, and therefore both of these operations are going to be logarithmic. Right? And so we've got an efficient data structure here that allows us to put stuff in, and it allows us to take the minimum element out. So from that perspective, a heap is a restricted access data structure, just like a stack or a queue. In other words, the operations that it's intended for are efficient. Of course, it's still a binary tree. We could perform a pre-order traversal on this. We could perform to do an arbitrary search. We could do a bunch of different things, but they're all going to end up being linear, order n, because if you have to examine every single node in here, then there are n nodes, and it's going to be order n, right? So we don't have the ability to arbitrarily insert wherever we want. We don't have the ability to search for things anymore, like a binary search tree. But we do have these 2 restricted operations that are guaranteed to give us a very, very efficient way of doing things, right? We can insert the new node as the next available spot, then heapify upwards. All right? Those are the 2 ideas. Those are the 2 ways that you, the 2 operations that that support a heap. Let's talk a little bit about the implementations, and then let's talk a little bit about the applications of these things. Now, first of all, I drew it as a tree, so you can implement a heap as a binary tree. We could go back to Eclipse, and we could do another subclass of our binary tree and call it a heap. And both of those operations can still be made efficient. It's just a lot more complicated. That if you have a tree structure where you've got nodes and left children, right children, and parents, then you can determine. Well, you always have access to that root, but you don't necessarily have access to the last element. Or the next possible gap. Like if I were to insert now, it'd be the left child of 9 here, but I haven't left myself enough room here. You can keep track of those or recompute those in order log n time. And if you're interested in the mathematical trick to do that, go ahead and read the book chapter that covers it. But what I'm going to do is I'm going to show you a different way of doing this. Okay. What I want to do first is I want to make an observation about what if we were to perform a BFS traversal on this. You would start at the root, and you would read everything at the first level, left to right, then the next level, then the next level, then the next level. I'm going to take that BFS, that breadth first search traversal, and I'm going to put it into an array. Okay? But instead of starting at 0, here's my index up here, I'm going to start at 1. Right? Just to demonstrate this. All right? So 1, 2, 3, 4, 5, 6, 7, 8. I don't know how many things I put in. We might need more room here. Right. But here's the BFS traversal. 1, 2, 7, 10, 5, 9, 15. Oops, 15, sorry. 50, 20, 8, and 100. And then maybe it goes off and we've got more room here. It's kind of like an array-based list where you have a larger capacity, but the number of things that you're actually holding in here is only 11 things that we're holding in here. Okay. Now, that's actually how that's actually the implementation of a heap. We use an array. Here's the trick. All right. If we've got a node u at index I, what we need to be able to treat this as a binary search, as a binary tree, right? Maybe its parent, it's a left child, maybe it's a right child. I'll go ahead and draw it like this. Right? There's its parent, there's its left child, potentially. It may or may not have a left child, may or may not have a right child. But of course, if it has a right child, it has to have a left child because of the fullness property. So if u is at index I, where is L located? So let's look at an example here. 1 is at index 1. Where is its left child located? It's at index 2. Right? And 1, 2, don't worry about those. This could be 0, or this could be -10, and this could be -5, right? Or don't worry about that. These matching does not mean anything, right? All right, where is its right child? Well, it's at 3. Okay. Let's look at another example. 2 is at index 2. Where's its left child? It's at index 4. Where is its right child? It's right next to it at index 5. Because of the way that we drew this tree, took this BFS traversal and translated it over to an array. Let's look at one more example to see the pattern here. 5 is at index 5. Its left child is at index 8. 10. And its right child here, 100, is right next to it. Right? So hopefully you saw the pattern there. That if this is at index I, this is at index 2i. In other words, all we have to do is double it up and jump. Right? Here's 2. Its left child was at index 8. Sorry, that's not duh. 2 times 2, double that up, it's at 4. Right? I wish I had not done that in Sharpie. And where is its right child? Well, it's right next to it. And so that's going to be 2i plus 1. Right? Ignore that. The other example that we looked at was 5. Right? 5, if I jump to 2 times 5, that's going to be index 10. And then right next to it, plus 1, is going to be index 11. That was 8 and 100, the children of 5. Right? And you can also work backwards. Say that I've got 8, or 50 here. At index 8, how do I get back to its parent? Well, all I need to do is divide by 2. But you have to be careful here, because what about its other child? The right child of 2, right? Or the right child of 2 was 5. 8 divided by 2 is 5, or is 4, so it's over here. Let's go 2, though. 4 goes back to 2. Its right child here is at index 5. 5 divided by 2 is 2.5, which is no valid index. But I want to jump back to the same index here. So the trick that I do is just simply take the floor of that index. Right? So a really, really simple implementation here. And it has the added benefit that, remember the 2 assumptions that we had for the 2 basic operations, the get min and the insert? The idea here is that I always have access to the root because it's always going to be at index 1. I always have access to the last element and to the next gap as long as I keep track of the size of the heap. And I update it. Anytime I insert something, I increment the size of the heap. Anytime I remove something, I decrement the size of the heap. Looks like we do have an online question here. Right? Yes, thank you. 2 times 8 is equal to 2 times 2 is equal to 8. Confirmed. That will be on the final. Remember, there is no final. Right. Okay, so there. You guys are lucky you're anonymous on there. All right, so there's our implementation. All right, we might, if we have enough time today, I'll go ahead and take a look. right? We might try an implementation there. But what I want to do is I want to look at potential applications of this. Okay, and for that I'm going to go back to the main screen here. Right. So let's talk about applications. So remember way back when we covered queues, we covered one variation on a queue that was a priority queue. Right? Remember that with priority queue we needed to insert things according to a priority. And we needed to remove the next highest priority element. Highest, lowest, it doesn't really matter. Again, you could, when you do this, you do it with a comparator, and so you just flip those around. This is a perfect application of a heap, because of course we can insert stuff, and it may not. It's not going to be a list like your sorted list ADT that you probably did for your project. It's not going to insert it at the end and then move it to where it needs to be. It's going to throw it on top of the heap, and then it ends up, like a real heap. If you throw something on top of a pile, then you don't know where it ends up, but the heap property will be satisfied. We also have access to the highest priority element at the root if we have a max heap, or if you want to flip that around and do a min heap instead. It offers both operations. Offers both operations, both efficient operations. That is order log n operations. Right? So it's a perfect application, or it's a perfect way to implement a priority queue. And in fact, in Java, that's how it's done. There is a priority queue implementation. Guess what's in Java and in a lot of programming languages? How do you think it works? Well, it works by implementing a heap. Okay. Another application. So if I've got a bunch of stuff in a heap, and I start taking things out one by one, right? For example, let's go back. If I start at the top and I take out the minimum element, right? And then something comes in and, heapification, it comes back in and it fixes the heap. Then I do it again. I took out the minimum element, then I take out the next minimum element. Then I take out the third minimum element, and I take out the fourth minimum element. What am I doing? The order that I take stuff out, it ends up being the order that it would be if it were sorted, right? So, heap sort. Right? Simply put stuff into a heap, take stuff out of a heap, right? So let's go ahead and take a look at maybe the pseudocode over here for doing that, okay? So here's Heapsort. So H will end up being a initialize a min heap, right? And you could set that up really easily. So now for each element, so the input here is going to be A, which is a bunch of things A1 through AN. Doesn't matter what those things are, again, pseudocode. For each A in A, H, and I'll call it insert A. Right. That's it. I'm putting stuff in. Okay. Then for each X in H, in other words, you could change this into a while loop. While H is not empty, then I will take it out, right? In fact, here, let's go ahead and rewrite this. While H is not empty, we can go ahead and get X. Actually, I'll just call it I, A sub I. Will be H dot get min. Right. And then I'll increment an I here, my index variable. We can initialize it up here to be 1. Right. There we go. So what is this doing? It's putting everything in, filling up the heap. Right? And then while there's still stuff in the heap, you just take things out. Take out the minimum, take out the minimum, take out the minimum. So A1 will end up being the minimum. We increment this. A2 ends up being the next minimum. A3 ends up being the next minimum. A4 ends up being the next minimum until at long last you output the variables that you just set, A1 through AN. This is what I generally like to end the course on, in that it goes all the way back to the beginning of the course. Remember that one of the mantras, one of the themes of this course is that smart data structures and dumb code are a lot better than the other way around. This is dumb code. Put stuff in, take stuff out. Put stuff in, take stuff out. That's all you're doing. You are relying on the smart data structure, the heap here, to end and the properties of the heap to give you an efficient sorting. Right? We do have to make sure that this is efficient, though. So I'm going to go ahead and focus on this first one right here. Right? What's the efficiency of this? Right? You're inserting stuff. So one way of looking at it is that you insert n elements, and each insert is at most order log n. Right? Now you can do a little bit closer, amortized analysis of this, and if you're interested in that, please again read the book or watch the pre-prepared videos, because I do go through that. Basically, you're not paying log n every single time, the number of comparisons at least. If there are only 5 elements in there, then you're only paying log 5 number of comparisons. If there are 50 elements, then it's log 50, right? As it grows, as you put stuff in, the size grows, but once at most, the size is, of course, n. Assuming that everything is started in there to begin with, then it costs you at most to insert something log n. In other words, i.e., the entire process here is going to be order n log n, right? Which matches the efficiency of quicksort, merge sort, and the fast sorting algorithms that we looked at. But I would argue that this is much better code-wise because you are using a smart data structure to get the job done. Smart data structure, dumb code. It's a lot better than the other way around, like quicksort, which is very clever code. It's got a divide and conquer, this partitioning subroutine, right? Very, 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 very clever. But you're using recursion. You're exploiting the call stack, et cetera, et cetera. You're not using any data structures there whatsoever. Right? And by the way, this one is also going to be order n log n for taking stuff out, because you have to get the minimum. You pull that out. You have to fix it, so that's going to be log n. You do that how many times? Well, you put n things in there. You're going to take n things out, so therefore you perform n get min method calls. Each one of those method calls is going to be order log n, and so together it's going to be n log n. So you've got 2 n log n, but remember, big O analysis, we don't care that there's a constant factor out there. Okay? So, super efficient way of sorting stuff. We do have some time, so if we want to, we can go ahead and go back to Eclipse here. And, all right. And let's try to do a really quick heap implementation. May not necessarily get all the operations working here, but let's go ahead and try. I'll call it. I'm not going to inherit from a binary tree because I'm not using a binary tree representation of my heap. Again, that is possible. Check out the book. We go through some mathematics for figuring out, is the gap on the left subtree or the right subtree? Then you traverse and you ask the same question again, and you eventually get down to the last element or the gap in order and a log n time. Right? What I'm going to do here is I'm going to take a little bit of a shortcut, and I'm going to have an array list as my internal representation here. So private final array list. And it'll hold elements here of type T. So I'll go ahead and parameterize this as well. Right? I'll just call it list. Right? There we go. I'll go ahead and import this. There we go. And I'll go... yeah, we'll also want a comparator for elements of type T. And I'll just call it CMP. And so public heap will take in that comparator. And we'll initialize the list in here. And normally what I would do is I would say that I would make this into a list, right? And then have the array list as an implementation of it. But I really want to make sure that it's an array list here. If it's in a linked list, then you don't have random access. So you can't do that trick of where's the left child? Well, it's at 2i. If you're at index I, you can jump to 2i. If it's at you can jump to 2i plus 1. You can't do that trick with a linked list. So I definitely want to make sure that that's an array list. Okay. Import that, and this.cmp is equal to the given comparator. Okay. I'm going to go ahead and borrow the demonstration over here so that we already have an integer comparator. Oops. There we go. And we don't want a binary search tree anymore. We'll go ahead and have a heap. Right? And there we go. And then we'll figure out this stuff later on. Okay. So there's my initial way of representing this stuff. Now let's go ahead and look at one of the insertion. Let's do the insertion method because we've got to get stuff in there in order to test it, right? So let's go ahead and go with a public void, or we could go with a Boolean, right? We added something. Insert. Now, with a heap implementation like this, allowing duplicates, well, the first thing you have to do is determine is 5 already in the heap? And if it's not, then we'll reject it, right? Well, that means that you have to search through and determine is 5 already in there. There are tricks that you can use to reduce that complexity, but unfortunately, you're not going to be able to do that in general efficiently. So what we'll do is we'll just have it be void and insert an element of type T item. Oops. Okay. So remember how this worked. We need to insert it at the last possible place. So with my list implementation here, the list.size, I'm gonna reuse that. How many things are already in there? If there are 5 things in there, remember it starts at index 1 because we burned that 0 index. So 1, 2, 3, 4, 5. Where does it need to be? It needs to be at index the size plus 1. Right? So this dot list, I could set it, or I could just go ahead and add it, right? And it'll take care of it for me, right? I forgot. I'm in the mindset here that we're actually using an array instead of an array list. I don't have to worry about the indexing. It takes care of it for me. It adds it to the end of the array list. Okay, but now I do have to heapify it up. I have to make sure that I look at its parent, right? And if its parent is less than the element than the current item, then we need to swap them. All right. So I do need to keep track of the index here that I just added it at. So int, we'll call it I because that's what I was using in the demonstration. This dot list, since we've already added it, dot size, that will be my current index. I don't have to go +1 because if there are 5 things in there, now there are 6 things in there, and it's at index 6. Sorry. All right. I do need to make sure though that I burn that first index. This dot list dot add, I don't know, null. Right? An array list does allow you to hold null elements, so we'll burn the first index like that. Right? Now what I need to do is I need to go up to its parent, right, and see is that parent less, right? So int parent index will end up being math.floor of I. Oh, I need to make sure that that works. I divided by 2. There we go. Let's see. Yep. Great. All right. So that takes care of the division and the floor for me. Right? And then, of course, I'm not using it. And I need to check if the parent, if the thing's stored at the parent index. So I need to use my comparator. The thing stored at the ith index. So this dot list dot get the element at the ith index, and compare that to the list of the parent index. Right? And let me go ahead and give myself some more room here. There we go. If that is, let's see, we need to make a comparison here to 0. So the current one is less than the parent, then we need to swap them. So less than the parent would be less than 0. There we go. Okay. Then we swap. And you can very easily swap with a list, this dot list dot swap. Nope, we don't have a swap method. So t temp is equal to this dot list dot get I. And then we'll set the parent index to I. This dot list dot set is what you want. We want to set the thing at the parent index to temp. Oh, no, wait, I first, sorry. I to the thing at the parent index, so this dot list dot get parent index. Right. And then this dot list dot set the element at the parent index to temp. Right. That's swapping right there. Okay. And that's only one operation. Right. Now we need to repeat that. Now we need to update the parent index here. So I need to jump up to the parent. I is going to end up being the parent index. Right? And I need to repeat this process again. And so I would recompute the parent index, and if it's less, then I will go ahead and repeat it. But of course, I want to put this into some sort of a loop. I wrote the body of the loop here just to get it straight. What we want to do is we want to make sure that we are continuing until I is, if I goes past 1, right? We go to 0, or we go negative, or somehow get down to 0. Then I want to make sure that I stop because I've heapified it all the way back up to the root. Or if this returns something, if it returns something positive, then I want to stop. Okay. So let me go ahead and put my loop condition here. While I is greater than or equal to 1. Right? Nope, because once it's 1, I don't need to look at its parent anymore. So while I is greater than 1, right? It's down here somewhere, and so we do need to look up. And then I will put this comparator over here into the actually, no, I won't integrate that. I'll go ahead and do it like this. This is my stopping condition for getting up to the root. Okay, and then I will compute the parent index. Right. Now let's think about this. If I is say 2 or 3, then it ends up being 1. And then you look at the parent and it's 1. And I ends up being 1, and so this is no longer true, so you break out of this. Okay, I like this. I don't have to integrate this comparator anymore into my while condition. Right? And then I can return. Right? Hopefully this is correct. I didn't practice this before. I didn't plan on getting this far, but let's go ahead and test it out. So come down here, and it's no longer T. Let's call it H because it's a heap, right? H. And let's do a toString method here so we can actually take a look at what it is. I'm just going to go to file, source, generate toString method, And I'm only going to do the list here. In other words, I'm just going to print out the list. Right? Okay. So let's go ahead. Well, let's go ahead and make sure that our initialization works. And we've got, yeah, of course, an empty heap there. Then I can go ahead and add stuff to it. So for int I equals 1, I is less than or equal to 10. We'll just go ahead and insert 1 through 10. Make sure that it's a heap afterwards. I plus plus. Of course, normally I would go into a I could insert random things into it. In fact, we could do that. Random r is equal to new random based on the current system time. Int x is equal to r dot next int, and then h dot insert r. There we go. Oops. What's wrong with you? Oops. Not r. There we go. All right, let's see if this works. Ah, darn it. We've got a 2. Index 2 is out of bounds for length 2. Okay. So, where is that happening? Well, okay, I don't want that. The internals there. I want on line 24. I should have practiced this. So the parent index I is going to end up being the... Oh, that's because we need to... okay. So if it's just the size, then remember, so we inserted something, and the size is actually 7. So we would need to... darn it. Not size, but it's going to be 5, 6, 7, minus 1. So let's start at minus 1 here. I do need to start at minus 1. Let's run this again, see if that fixes it. Aha! It looks good, but darn it, those are stupid numbers. I'm not going to be able to visualize and see that that's a min heap. So what I'm going to do is I'm going to make sure that they're at most 20. Right? That'll allow us to visualize it and see if that actually works. Right? Excellent. So 0 is definitely at the top. Then its child is 6 and 4. In fact, what we can do is we can, I'm going to, if you have a piece of paper and are following along, try to draw that as a tree. Right? Remember that null is just burned. That 0 ends up being our root. 6, 4 are its children. And then 7, 13, 13. So 13, 10. 8, 8, and 15. And there we go. There's my drawing of it. And that is definitely a min heap. So we were successful in having a really quick thrown together implementation of a heap with an insert method. What I'm going to do is I'm going to let you do the exercise of doing the get min and then heap correcting it. All you have to do is save that off into a variable, grab the last thing, and because it's an array list, you know how many things are in it. You just need to adjust for that -1, and you put that at index 0 instead, and you remove this, and then you just need to do what I did with a while loop, but in reverse, making sure that you heapify this 15 downwards. Right? I'll leave that as an exercise for yourselves. And in lab tomorrow, we already have a created heap implementation for you. In lab tomorrow, you'll go ahead and continue and use that to solve a problem with Heapsort. Okay. I do want to mention though, now that we're at the end of looking at these things, don't roll your own, right? Let's check and make sure that nope, still no. Just the same comment there. So I do want to mention that in practice, you don't roll your own. You don't create your own heaps. You don't create your own implementations in general. So what about a binary search tree implementation in, say, Java? So there is this thing called a TreeSet. Let's go to it. And a tree set is a balanced binary search tree implementation. In fact, it's a red-black tree the last time I checked it out. And it implements an abstract set here. It implements the sorted set implementation interface. So in other words, it keeps it sorting. It does in-order traversal if you're going to use it in an enhanced for loop to give you the elements in order. It does use a tree structure. That's why it's called TreeSet. And it offers guarantee insertion is going to be. In fact, I think hopefully it says it right here in the documentation log. There we go. The implementation provides guaranteed log n performance time cost for the basic operations of add, remove, and contains. So in other words, insert, delete, and search. That's all going to be order log n. Because it's a balanced binary search tree implementation. I believe it's a red-black tree that if it gets too skewed to one side, it ends up rebalancing, so that it's not a guarantee to be a full tree, but it is guaranteed to have a depth which is proportional to log n. What about heaps? What about a Java implementation of a heap? Java priority queue. Right? Turns out that the priority queue implementation of Java uses a heap under the hood, so you can use it as a heap, right? Let's see, where does it say heap? Right? Yep, an unbounded priority queue based on a priority heap. So again, it takes a comparator like our implementation here. It probably does it a little bit better, a little bit more optimized. But otherwise, you've already got these things. Don't roll your own. You've already got linked lists. You've already got array-based lists. Any data structure that you can come up with, there's probably going to be a version of it in the collections library, as well as several variations for you to use. Don't roll your own in practice. Okay? When we come back on Thursday, after your lab of using both binary search trees and implementing a few of the operations, as well as heaps, and solving a problem with them, then we'll have basically a course retrospective. It's just a nice thing that I like to wrap up the course as and remind you of what you've learned this semester. Okay, so have a good lab tomorrow and have a good rest of your day.